Hi guys, in this video we're going to be looking at graphing and solving quadratics again, but we're going to be looking at them in what I would call proper standard form. So up until now you've heard me call this more than once standard form, and that's just because of how a textbook refers to it. But what I'm going to tell you is that we're going to henceforth call this vertex form, just because it really just tells us, where our vertex is at h and k, which kind of helps us find our axis of symmetry as well pretty easily. And so vertex form is great, but what we might acknowledge is that if something's in what we call proper standard form, we would have to take the time to complete the square in order to write it in vertex form. And that's not always actually a pretty number, or you get pretty values when you do that. And so we have to look at an alternative to using completing the square to write it into vertex form. And so that is to look at just what are some properties of quadratic graphs and equations when we just leave it written in what I'm going to call standard form here. So first things first, I want to make sure that we're straight on something here. We're going to refer to this henceforth as standard form, or what I'm calling proper standard form here, where we just have a quadratic trinomial in this ax squared plus bx plus c form. Most importantly, being able to identify these coefficients here. And so one thing that I want to start with is just that when we look at functions like this, our vertex is at a very interesting value. It's b negative b over 2a here. And that's the x value of our vertex, meaning that if we take the opposite of this middle term coefficient and divide it by 2 times the leading coefficient here, that's the x value of our vertex. And so where would the y value be? Well, for now and for always, we're going to write this f of negative b over 2a, which basically acknowledges is if I know where the x value of my vertex is, I could just go plug that into the rule for this function, and that's always going to tell me where the y value is. And so if that's the case, then we might as well acknowledge one other thing, that our axis of symmetry has to go to the same x value as our vertex's x value. And so I'm going to write, and let's put this maybe in a blue color here so we can distinguish, negative b over 2a. So it's important we know that that's always the x value where our vertex lies. So I'm going to go ahead and make just like a quick sketch here. But let's say we have some quadratic function that is cruising down here. We would want to make sure that we highlight some things, including the vertex. And so we say the vertex, again, is at negative b over 2a, is its x value. Its y value is the function value at that x value when we plug it in. And also its axis of symmetry. And so axis of symmetry is always very easy. It is the same x value as the vertex's x value here. And so again, we're going to really be in a constant struggle for, let's find some zeros here, but ultimately we want to know that the graph looks like this if it's in standard form, and we're going to have to make some sketches here. So what I want to do first of all is just make a sketch of this graph here that's in standard form that looks like it would be really not fun to complete the square on, to put it in vertex form. But when we find that graph, we're going to use it to kind of estimate our zeros, and then we're going to verify all this algebraically with, you know it, dun dun dun, the quadratic formula. So what I'm going to do is scroll down a little bit here, and let's take a look at making our sketch. And so first things first, I want to start with the axis of symmetry, believe it or not. And the reason why here with things in standard form is just because the axis of symmetry is going to tell us the x value where our vertex lies. And so I know it's negative b over 2a, and I might as well put this somewhere now. Our a value is positive 3, our b value is positive 2, and our c value is negative 4. I'm going to make a little box over here. So if we do opposite our b value over 2 times our a value, and I have to erase this here. I meant to put parentheses. We get 2 here inside these parentheses, and then a is 3. And so what this comes out to be is negative 2 over 2 times 3, which is 6, which is negative 1/3 here. And so yuck means negative 1/3 is our x value of our vertex. And so vertex wise, I suppose that we are going to have to acknowledge that negative 1/3 is the x value, and the y value is what we get when we plug this into our function here. So I didn't anticipate this, but you know what? This will be good exercises with our fractions here. Let's find f of negative 1/3, which would mean we get 3 negative 1/3 squared plus 2, big 2, times in parentheses negative 1/3 minus 4. So simplifying this, let's do our operations first. Exponent If we take negative 1/3 times negative 1/3, we get a positive 1 over 9 if we multiply those straight across. Here we get a negative 2/3 when we do this. And then I'm going to go ahead and write this right here, as a matter of fact, as thirds. So if I take 4 over 1 times 3 and times 3, I get 12/3. Looking at this now, okay, I suppose this is going to become here a positive 1/3. And when we take that positive 1/3 plus a negative 2/3, positive 1 and negative 2 is a negative 1. Negative 1/3 plus negative 12/3 is negative 13/3. Ooh, yikes. So that means that our vertex is at negative 1/3, negative 13/3. Or, if you like, we could say negative 1/3. And 3 goes into 13 4 times. So negative 4 and 1/3. We're going to go ahead and make a sketch of this here. And so, looks like we would be going down, if here's negative 1. Say 1, 2, 3, 4, negative 5 here. We'll use a different size scale. But down negative 4 and 1/3, we'd be about right here. And our A value here, to begin with, was 3, so we'd go about right 1, oops, not negative 1, down 4 and some change, negative 1/3, down 4 and 1 some change. So we have to go, let's see, from here, if we go 1 unit to the right, we'd be about right here before this notch mark, and we're going to go up 1, 2, 3-ish. That would put us about right here. And because of symmetry, we would go about 1 unit to the left here and then up about the same height. So sorry, negative 1, I'm going to get up in your space. But we get something that looks like this here. So my first inclination is to say we have one between negative 1 and negative 2. And we have one between 0 and 1. That's kind of like where my brain's at here with what our sketch looks like. When we look at solving any quadratic that's in standard form, I will tell you this, it is worth knowing your quadratic formula because, and we're going to write this down here, the quadratic formula says if, get this down, we say ax squared plus bx plus c equals 0. This is an if-then. We say then the zeros are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so something worth mentioning here is actually this. This first part, negative b over 2a, is basically an acknowledgement that, let's get back up here, that this is the x value that kind of splits right between these two zeros. And if you were to take that negative b over 2a and either add the square root of b squared minus 4ac or subtract the square root of b squared minus 4ac, you would be going left or right of this negative b over 2a by that amount and landing at the zeros here. And so we're going to use this to help us solve this equation. The bad news is I'm going to have to flip over to another page here. So our coefficients are 3, 2, negative 4. Let's go ahead and take a look at on this canvas here. We say a is 3, b is 2, and c is negative 4. And I'm actually just going to verify this for us here. 3, 2, negative 4. We're going to go ahead and put this in then into our quadratic formula. And so I say I always kind of go negative b over 2a. You know, I keep that in my back pocket. But then we have the square root of this, b squared minus 4ac. Let's go ahead and put in our coefficients here. So we have b and b here and here. We have a and a here and here. And then c is negative 4. We need to just then work on simplifying this and then using it to find some decimals. So negative 2 out in front and 6 on the bottom. Now we can worry about this inner part of our radical, which we actually give a name. I'm going to write it here. It's referred to as the discriminant. And the discriminant is this b squared minus 4ac. We really like this number because if it's positive, it just tells us we get two real solutions. You know, positive square roots. If you take square root of a negative, you know, if this is negative, we're going to get two imaginaries. And if it's 0, it's kind of cool because you get the same answer twice, the same real number twice. So we get 2 squared. I always look at this as a negative times a positive times a negative. That's going to mean the whole thing's positive. And I kind of look at this then at 4 times 3 is 12. 12 times 4 is 48. And so we're going to always usually need to rewrite this on several lines of your paper. Suppose we get 52 here. A rule is we can't leave any perfect square factors inside of a radical, and so I recognize, and you would want to check it out too, investigate, but I recognize that 4 is a factor of this. I always think about decks of cards. There's 4 suits and 13 in each suit, but there you go. And I know the square root of this is 2, so I'm going to rewrite this so it looks a little cleaner. Negative 2 plus or minus 2 times the square root of 13 all over 6. Now typically, I want to show you what's happening here. The top, both of these terms have a common factor since they're both 2. And so I could actually factor out a 2 out in front, and I get left with -1 plus or minus 1 square root of 13. And this would be all over 6. And then I could cancel out common factors here, like make this a 1, make this a 3, and I'd be done. Okay? But what I want you to know is it's a little bit easier sometimes to just recognize that, hey, these two things on top also share a common factor with this on bottom, and it has nothing to do with what's inside of this radical, it's what's out in front. So I'm actually going to all at once say everybody on top, every term on top, and every term on bottom share a common factor of 2. We're going to split them all in half then and make this -1. This would be a plus or minus 1, and then root 13, and this would be a 3. And so our two zeros are -1 plus or minus the square root of 13 over 3. And I'm going to go ahead and leave it in this form just because, again, you've seen me do this on a calculator last time. It's a little bit easier to type this in. So let's get your calculator ready here. Turn on, clear this out. And we're going to type in then need parenthesis first. -1 plus the square root of 13, square root 13, end parenthesis, all divided by 3. I'm going to get this, and then I'm going to hit second enter and go back and switch that beginning operator to a minus. And so going and looking at our sketch here that we had on this other canvas, we had sketched it right here. And so do our decimal values verify this or back it up? And so it looks like we have one between 0 and 1 right here, and this would be this if you're looking at the calculator, about 0.87 here, and then our decimal on the left, -1.53, that would be our 0 on the left here. So just keep in mind that sometimes it's going to be painful to put this into vertex form by completing the square. Even though completing square is perfectly fine and it works, it might be easier to just go ahead and use your quadratic formula to do that. And it's also important to note we know how to sketch one of these by knowing where its vertex and axis of symmetry lie if it's in standard form.